Distinguished guests, ladies and gentlemen, welcome to today's session on global change and globalization. Certainly a topic which no doubt is one of the most intriguing and also one of the most disturbing of our time. Especially I want to welcome our two speakers today, Eduardo de Mulder and Bruno Messerli. It's great to have you here. Eduardo de Mulder will start our session today with his talk on global planetary change and human globalization. Ed de Mulder, born in the Netherlands, is a geologist with wide-ranging interests in other fields as well. After obtaining his MSc degree in geology at Utrecht University in 1971, he completed his PhD thesis in 1975. In the same year, Ed de Mulder joined the Geological Survey of the Netherlands, an organization and its various successors he served for many years and in many different leading positions. In 1998, Ed de Mulder was appointed professor in subsurface management at Delft Technical University, and in 1999 he was appointed chair of the Delft Cluster Program on subsurface management. Over the years, Ed de Mulder has also been working as a senior advisor for several departments of the Netherlands government, the United Nations, and the European Union. In August 2000, he was elected president of the International Union of Geological Sciences, IGC, basically to raise the profile of geosciences and to motivate students to embark on a geo-professional career. He launched the initiative to proclaim the International Year of Planet Earth at the onset of his presidency. He also chaired the International Year of Planet Earth, IHPE, management team until the UN proclamation was accomplished, and from 2007 to mid-2010, Ed de Mulder worked as an executive director of the Secretariat of the International Year of the Planet Earth, based in Trondheim in Norway. In that capacity, he led a team that organized the global launch event held 2008 at the UNESCO in Paris, and he also was responsible for fundraising of the international activities and for the creation of national International Year of Planet Earth committees in 18 nations and regions around the world. In 2010, he developed a follow-on initiative, eventually registered as the Earth Science Matters Foundation, for which he acts as the director of its secretariat. Ed de Mulder has been honored internationally with many prestigious positions and awards. Moreover, he published more than 120 widely received scientific articles and books, mainly on applied geosciences topics. Professor de Mulder, I'm eagerly looking forward to your keynote lecture titled Global Planetary Change and Human Globalization. Please join me in welcoming Professor de Mulder to our conference.
Good afternoon, ladies and gentlemen. Many thanks to the organizing committee for inviting me here to give a speech for so many people on this topic, global planetary change and human globalization. In just 50 years' time, the world has changed dramatically. So just to get, I have to learn it. Yes, okay. For the first time ever, we could see our blue planet from outer space following the launch of Sputnik in October 1957. By that time, new scientific evidence had been collected to prove Alfred Wegener's theory of continental drift. Knowing the mechanisms driving this phenomenon caused a paradigm shift in the earth sciences. This year, we celebrate the 100th anniversary of this landmark publication. Yes, the world has changed indeed. Humans became a geologic factor, beginning to interfere with the natural earth forces and started to make distinct human imprints on geographic maps, igniting a new era on the geological timescale, the Anthropocene. These observations may trigger us to raise some big questions about our planet and how we, humans, interact with it. Today, I would like to share with you some of these questions. So, what do we know about planet Earth today? How do we, humans, interact with system Earth, and how would that impact its bearing capacity? How can we, Earth scientists, that means geologists and geographers, contribute to sustainable development? But before taking off and diving into our planet's interior, a few words of caution and relativism. I said that we, humans, have become a geological factor. So we do generate modifications in the topography of riverbeds, coastlines, sediment budgets, permafrost thicknesses, etc. But I would also like to stress that by all that, we are not really changing or threatening our planet as a whole. Human activities do not yet trigger major tectonic forces as continental spreading, mountain building, nor the convection currents in the Earth's mantle. Yes, we may ignite small earthquakes by extracting natural gas and oil from deep reservoirs, or by loading the surface with giant water reservoirs for hydropower generation. But these impacts are confined to the upper parts of the Earth's crust only, at a maximum to about 6 kilometers. Please keep in mind that it's just 1 per mil of the Earth's diameter, which is 6,370 kilometers. There are no indications that impacts of human activities would reach much deeper soon. Yes. So what do we know about our planet Earth today? Speaking about planet Earth, we should be prepared to look downwards first. Down to Earth is the title of this Congress. But many people have mixed feelings about the subsurface. The realm below our feet is often perceived as the domain of scary creatures, darkness, dirt, danger, evil, decay, and death. The underground has a negative connotation. The public, including many intellectuals and policymakers, has generally no clue about the subsurface, let alone the processes that govern it and how these may determine their lives. Perception of the underground may vary with cultures. In this picture, Pachamama, its planet Earth, is being worshipped by cultures in the Andean region. This is from Bolivia. So what do we really know about our planet? Anyway, a lot more than 50 years ago. We have witnessed revolutionary progress in our knowledge of this planet. Here I will focus on 2 aspects, on the anatomy and composition of our planet, and on the processes. When I was a junior field geologist, quite some time ago, I was involved in geological mapping campaign in our Dutch swampy deltaic area, with a lot of ditches to jump. The subsurface was primarily explored by making drill holes, mostly by hand, and describing the sediments in a small booklet. From these notes, we made geological sections, and eventually these were compiled in geological maps, which are basically topographic maps with the shallow geological conditions printed on top of that. Making such maps was a national responsibility, and every country did that in its own way. Today, geologists still go in the field and make such boreholes, but these are part of a wide array of other sources of information, including geophysical and remote sensing techniques. Through GPS, all data are sent in 3 dimensions to a station which automatically plots the data points on a digital map and stores the geological information in large digital databases. From these databases, many types of geological maps can be produced almost instantaneously and for various public applications. In the next few years, all companies and organizations that penetrate the Dutch subsurface are forced by law to copy these new subsurface data in this public database. Vice versa, all public organizations wanting to construct anything in or at the ground will be obliged to check the existing subsurface information first before building to avoid redundant penetration of the subsurface. Moreover, since the launch of the International Year of Planet Earth in 2007, geological survey organizations in 117 countries embarked on the One Geology program. That program aims to make all geological map information digital, and by translating that into one singular computer language and legend, and this will result in a digital map of the world, including the oceans, with free access for all participating nations. Eventually, One Geology will provide a real third dimension to international geographical search systems as Google Earth. Such digital geological maps provide information about the structure and composition of the upper parts of the Earth's crust. But if we speak about the anatomy of this planet, we must look much deeper as well. In the late 1960s, Earth scientists began to apply scanning techniques used in the medical sector for geological purposes. Seismic tomography was born, which identifies seismic anomalies to depths of about 2,000 kilometers deep in the Earth's mantle. Here. We may actually observe real-time how crustal plates are spreading and colliding, and how they are becoming absorbed by mantle materials in the subduction zones. Together and in combination, these techniques have made our planet far more transparent than when I was a field geologist. The resource industry has benefited enormously from such advances in technology and from the vastly increased understanding of the Earth's anatomy. Some of you may remember that the Club of Rome in 1972 predicted rapid and catastrophic depletion of the Earth's resources and, consequently, rising commodity prices. In fact, the opposite was true. Commodity prices dropped significantly and remained low for 3 decades in succession until they started rising again recently. Simultaneously, annual productions of such materials increased, but the world's registered reserves of most commodities rose as well. See this here. How come, as we are talking about non-renewable resources that normally would take millions of years to be created? This paradoxical situation may only be explained by new discoveries. New generations of geoscientists, using new exploration techniques, found large new resources of almost all metals and minerals, including oil and natural gas. Apparently, the Club of Rome did not include human resources, more specifically human ingenuity, in their still primitive 1972 computer models when predicting the future state of the planet. By today, the proven world reserves for crude oil are at least 40 years, as you see here. And there is sufficient natural gas available and accessible, economically accessible, on this planet for the next 100 years at today's production rates. So it seems that the Earth has very few secrets left. We roughly know how the Earth looks like and where most of its resources are located. As science and technology will continue to proceed, we may anticipate further transparency of our planet's anatomy and new discoveries of traditional and new commodities in the next few decades. By understanding the mechanisms that drive continental spreading some 50 years ago, we basically learned how our planet works. Supercontinent Pangaea broke up some 200 million years ago, resulting in the geographic distribution of today's continents. However, geoscientists soon realized that Pangaea had been just the last of a series of such supercontinents, and that there have been predecessors. The penultimate supercontinent is called Rodinia, assembled about 1,100 million years ago and broke up 750 million years ago. Now we know that there have been about 5 such cycles of supercontinent formation and successive breakups, all driven by convection currents in the mantle. Geoscientists keep busy exploring our planet for the oldest rock fragments from the oldest cratons and that constitute the oldest continents. Such cratons are about 3.5 billion years old, while the oldest rock fragments, some zircon crystals, so far identified, are 4.44 billion years old, just 150 years younger than the origin of the Earth itself. This is the grand story of the super large-scale processes that shaped our planet. But what about micro-scale processes? Just 3 decades ago, exciting discoveries were made at the grain-fluid interface level and about the active role of biota in such processes. Sediment particles interact with microorganisms and groundwater molecules with dissolved chemical compounds. As groundwater flows and its composition changes over time, such processes are never in complete balance. Quantity and diversity of microorganisms in the soil is enormous, and there is more life below our feet than above. Organic molecules degrade chemically or biologically. Recent research revealed that organic contaminants, like chlorinated hydrocarbons, may fuel biota with energy and carbon while degrading into less harmful products. Over time, any such contaminant will degrade. Soil biodegradation capacity depends on biota availability and on groundwater supply and discharge. This natural process might serve as a powerful tool for remediation policies. These findings gave a much better insight in the microscale geological processes and in the power of microorganisms in the subsurface. Knowing the basic principles of the Earth's processes and how the Earth works paves the way to forward modeling and predicting the impacts of human interaction with a much better known planet Earth. To that end, we will quickly review here some human factors and more in particular trends in human globalization or in global human behavior. Here we will discuss briefly 5 of such trends for the next decades. Well, let's have a look first at population. The UN predicts that 9.15 billion people, that's according to the mid-scenario, will live on this planet by 2050. From then onwards, this number would remain about constant until 2300, the year 2300. Until 2050, the Earth should just prepare for a 30% human population growth, and society should make room for accommodating its new inhabitants. Urbanization. The UN estimates again that in 2050 there will be 2.9 billion more people living in urban centers than today. That will boost the world urbanization to almost 70%. Now it's just above 50%. Ongoing urbanization will put major pressures on local geo-environmental conditions, and particularly to urban space, as there are often physical limits to urban growth. Urban land will become more and more expensive. Living standard. Living standard is normally expressed in gross domestic product per capita, adjusted for purchasing power parity, PPP. Oh, sorry. Okay, here we are. Yes. As a long-term trend, living standards have been rising for more than a century and a half. In particular after World War II. Between 1950 and 1995, living standards more than tripled both in industrialized and in the developing countries. And between 1999 and 2010, it almost doubled again worldwide. Simultaneously, life expectancy increased spectacularly. Today, people eat more and better quality food and use more earth resources than ever before. Environmental awareness. That began to develop since the mid-1970s and was converted into political action since the Earth Summit in Rio de Janeiro in 1992. Simultaneously, the media gave significant attention to the environment while fueling the educational systems worldwide. Environmental protection resulted in transforming large areas into natural parks or reserves, sterilizing these for other types of development. Concurrently, large areas of arable land degraded. Both land degradation and environmental protection added pressures to land development and availability of physical space for growing urban populations. And finally, science and technology. As mentioned before, so far, shortages in earth resources were overcome through science and technology, more in particularly by human ingenuity. The same holds for resolving major food security problems in Asia and Latin America through the Green Revolution. I'll come back to that later. So, in combination, these 5 trends demonstrate that urban space is becoming a more and more precious resource. This asks for unconventional solutions. And more people need more food and access to clean drinking water. More and wealthier people also demand for more Earth's resources, as everything that does not grow should be extracted from the Earth. The same people also produce more waste, which puts additional pressures on the environment. But on the other hand, there's one resource that's not under pressure. On the contrary, that is the human brain power. More people on Earth imply more potential human brain power and ingenuity. If managed well and in concerted action, this resource brought a man to the moon in 1969 and unraveled the human genome in just 10 years' time, developed a medicine that weakened HIV/AIDS, doubles integrated computer circuits in every 2 years, and combated hunger through the Green Revolution. In line with these achievements, and fueled by accessible data and information stored in ever larger databases, 30% more human brain power may quite well be able to resolve many of the anticipated challenges that the growing humanity will face in the next few decades. So what can geoscientists, geologists and geographers in particular, contribute to address such challenges? I recall what geoscientists have been doing and what we will continue to do: make the Earth more transparent, reduce uncertainty in prediction models, and better understand how our planet works. These steps in science and technology constitute the basic ingredients for finding new resources. The geoscientists will continue to do so by further improved technologies, and they will be successful as they did in the past half-century. They will thus bridge the time gap until next generations may fully rely on carbon-free energy supply. Future geo-environmental challenges will be combated by continuous investments in science and technology. Special attention should be given to the underground biota, which will probably prove to be a great new resource. Lack of urban space will be resolved by building more skyscrapers, but more interestingly, by building underground, where space is abundant and risks are low, while achieving very substantial energy savings. Over the past 10 years, excavating techniques have become safer, faster, and cheaper. China is taking the lead in this respect today, but also in Moscow, 15% of the new constructions is built underground. We geoscientists might know that what we may contribute to address such challenges, but unfortunately, the general public, nor the politicians and decision makers are well aware of this. That urges us to promote the use of earth sciences for society. Often, geoscientists were not quite successful in such endeavors. But that changed when the International Union of Geological Sciences and UNESCO began a worldwide campaign to raise public awareness for the important role of the earth sciences for society in 2001. I'm pointing here at the International Year of Planet Earth. For this enterprise, we used the successful German Jahr des Geowissenschaften in 2002 as a model. To implement at least part of our ambitions, we extended the period from 1 year to a triennium, 3 years, starting in 2007 and running until the end of 2009. The first step was to collect support within the GEO family. I'm happy to report that the International Geographical Union was one of the very first IGC unions that embarked on this enterprise by becoming a founding partner. 10 more such founding partners were identified, including all GEO unions and some major international geoscientific organizations. To collect the support from politicians, we approached the United Nations. That was done through UNESCO, our co-initiator. In 2005, the United Republic of Tanzania volunteered to be the UN member country to propose proclamation of the International Year of Planet Earth in the UN system. Following an intensive lobbying campaign in Paris and New York, the IYP was proclaimed by the UN General Assembly in December 2005. A separate non-profit corporation was then created with a board and a secretariat. The secretariat was based in Norway and sponsored by the Norwegian and Dutch governments. UN proclamation, in turn, triggered national geoscientific communities to create their own national chapter of the IYP. That was eventually done in 80 countries and regions, where tens of thousands of volunteers actively contributed to organize a wide variety of public events. In IYP, we determined 10 themes on the interaction between earth sciences and society. The megacity theme was spearheaded by IGU and more in particular by Professor Frauke Kraas. For all themes, brochures were produced and translated into 15 languages. The National Committee strongly focused on outreach, and that made the IYP particularly successful. We organized 3 major international events, and 45 nations did so at national levels. Such events were typically highlighted by the participation of national champions Politicians, presidents, and even a king made public statements in support of the geosciences in their countries, and so attracting significant media attention. The legacy of the IYP triennium has been abundant and very significant. It includes the emergence of the Young Earth Scientists group, YES it's called, with now 3,000 active members. And also, as I said, the One Geology project, which is a concerted action for a transparent Earth. Student numbers rose in at least 11 countries following the IYP. Several geoparks were opened. Scientific books were printed by Springer on almost all of the 10 themes, to mention just some of the many legacy items. The title of this presentation is Global Planetary Change and Human Globalization. I briefly discussed the global change of planet Earth throughout 4.5 billion years of its existence. Geoscientists found the roots of our continents and came quite close to its earliest beginnings. This demonstrates how rapidly the geosciences have evolved and that we are well on the way to understand how our planet actually works. I also showed that planet Earth has become close to transparent, from the crispy crustal plates into the rather viscous lower mantle. We need such knowledge to predict the Earth system's response to human-induced geo-environmental pressures, which have grown to geological dimensions. The important question is, how much geo-environmental pressures can planet Earth accommodate before its response may seriously affect our societies? That question basically points to the concept of sustainable development. Addressing human basic needs brings us to the second part of the title, human globalization. 5 trends in human globalization and development were explored, generating some future human needs and challenges: food, water, urban space, and Earth resources, and the surplus of waste. Human ingenuity, fueled by 30% more and culturally more diverse brain power by 2050, greatly ignored as a resource so far, will help addressing such challenges. Geoscientists trained in geo-environmental issues should play a major role. That role should, however, be better exposed to society, as was done, for example, during the International Year of Planet Earth. The IYPE served also as a model for an initiative by the International Geographical Union, a UN-proclaimed International Year of Global Understanding. This initiative builds on Brundtland's statement, "Think globally, act locally." The added value of the IYGU is including cultural diversity, which has been largely ignored in debates on sustainable development so far. Where crustal plates are driven by convection currents in the Earth's mantle, people are driven by their cultural backgrounds and roots, even in times of significant human globalization. Thank you very much.